So we are going to estimate the threshold voltage of MOS transistor. So what is threshold voltage? So it is the minimum amount of gate voltage required to create to establish the strong inversion situation. Okay, so it is the minimum amount of gate voltage required. How much amount of gate voltage that needs to be applied to establish the strong inversion condition. Remember that it's strong inversion. Okay, so that means the total bending in the energy band, it will be minus of 2 phi f. Okay, so that is the strong inversion condition. You know, we have discussed that in the previous class. So what are the components of threshold voltage? Okay. Now we are going to find out the different components of threshold voltage. So let us see. So the first component is the work function difference between gate and channel. Okay, that is phi ms or phi gc, or also we can say it is equals to flat band voltage VFB. Okay. So that means first thing is that you have to apply some voltage at the gate terminal to make the energy band diagram flat. Okay, because you know due to the work function difference between gate and the channel, okay, when we draw the energy band diagram at zero bias condition, there is a little bit downward bending is there. That is due to the work function mismatch between the gate and the channel region. Okay, gate and semiconductor region, substrate region. Okay. The first thing is that you have to make the energy band diagram flat. Okay. So this is the first component of the threshold voltage, that is the phi ms or phi gc, or also you can say it is VFB. Okay. So it is the work function difference between the gate and the channel. Second component is the amount of gate voltage required to establish the condition phi s equal to minus of phi s. That is total change in surface potential equals to minus of 2 phi s. Okay. So the next component is that amount of gate voltage required to establish the condition phi s equal to minus phi f. That means you have to bend the energy band. Okay. The threshold voltage related to the strong inversion, so you have to achieve the strong inversion condition, and you know that the strong inversion condition, that is total change in surface potential, will be minus of 2 times of phi f. Okay, this is the second component of gate voltage, threshold voltage. Third component, amount of gate voltage component required to offset the voltage developed by depletion charges. What is that? See, when you are applying a positive gate voltage, the first thing is that majority carrier holes, those are present near the oxide interface. Okay, because we have a p-type substrate. No? So the majority carrier holes are repelled back into the substrate. Okay, repelled back into the substrate, and they left some negative ions. And we have already discussed that situation in case 2 and case 3, that is carrier depletion and carrier inversion condition. So, and they left some depletion charge. Okay. So whenever there is a charge, so there will be some built-in voltage. So whenever there is a charge, there will be some voltage. Okay. So we know that from basic charge voltage relation, so Q equal to C into V. Okay. This is the basic charge voltage relationship, Q equal to C into V, or V, the voltage developed when the charge of amount Q is present. So the voltage developed, that is V equal to Q by C. So you can say there is a capacitor. Okay, so it's good amount of charge Q. Okay, the capacitance is C, and the voltage across capacitor is V. So V equal to Q by C. So similarly, when the depletion layer is created, so there is some depletion charge Q, that is Q depletion. So there will be some voltage component developed due to the presence of depletion charge. So that voltage will be Q by C. Okay, that means in our case, that voltage component V equal to QB0 by COX in our case. Okay, QB0 by COX. So where QB0 equal to amount of depletion charge inside depletion layer, okay, and COX, that is basically epsilon 0 into epsilon OX by TOX. So that is oxide capacitance. So you can check the equation C equal to epsilon A by D. So it is basically the capacitance of a parallel plate capacitor with unit area. Okay, epsilon into A, so we can write A by T, where A equal to 1. Okay, so oxide capacitance per unit area. Okay, so this is the expression for COX, that is epsilon by TOX, and QB0 is the total amount of depletion charge, and you know the expression for QB0, that is equal to minus root of 2Q Na epsilon Si. Of course, it will be multiplied by epsilon 0 into minus of 2 phi f at strong inversion. At strong inversion. Okay. So this is the third component of threshold voltage. Okay. So the amount of gate voltage component required to offset the voltage developed by depletion charges. So V equal to Q by C. Okay. Where Q, that is the depletion charge QB0, expression is this one. Okay. And C, that is the oxide capacitance per unit area, epsilon OX by TOX. So 0.1, 0.2, and 0.3, they are the major components of threshold voltage. Okay, they are the major components of threshold voltage. But apart from that, we can consider another one point. Okay, 0.4, the voltage component, of course, the gate voltage component. The gate voltage component required to offset or to compensate the trapped charges and or oxide interface charges. Okay. So actually, what is trapped charge or what is oxide interface charge? Now see, when the MOSFET is fabricated, okay, that means when we are going to deposit the oxide layer by using oxidation. Okay. Now there are different techniques to form the oxide layer. There is a dry oxidation technique, there is a wet oxidation technique, etc. So different technique is there, and you will study that in your VLSI technology subject. Okay. So remember that oxide we are going to deposit. So although theoretically we are saying that is a perfect dielectric, but inside every oxide, especially those who are fabricated during this MOS fabrication technique, okay, so there are some impurity, there are some defects. What I am saying that there are some defects or imperfections. Okay, so there are some oxide defects. Oxide defects means there are some voids, there are some vacancies, or there are some you can say empty states are there, they can capture the charges. They can capture the charges means they can capture electrons. Okay, they can capture electrons. So there are some electrically active defects inside the oxide layer. Okay, that is due to the mismatch in the crystal structure. Okay, so every oxide layer having this property, so they can capture some amount of that free electrons. Okay, so those defects are called electrically active defects. Okay, and the second thing, see, the interface between the oxide and semiconductor, so that is called the MOS interface. Okay, so we have a metal layer, then oxide, then semiconductor. So the interface between the oxide and semiconductor layer, so that is called MOS interface. Now see, we have a two different region. We have two different regions. So this is the oxide layer. Okay, this is SiO2, and this is the P-type silicon. Okay, this layer. So this is the interface. Now see, SiO2 is a different material having different electrical and its mechanical properties. Silicon is a different material having different electrical and mechanical properties. Okay, so this SiO2 having a different lattice parameters, means the crystal structure. This silicon having a different crystal structure, atomic size, etc. So when when they form the interface, okay, means the oxide semiconductor, this interface, okay. So due to the mismatch in the crystal structure, see, SiO2 is the oxide layer, it's a different material. Silicon is a semiconductor, it is a different material. So their lattice size, their crystal structure is completely different. Although SiO2 is the native oxide of silicon, okay, that mismatch is not too much significant. But instead of SiO2, if you use some other dielectric, such as hafnium dioxide, nowadays it is widely used. Okay. So there is some mismatch. There is some quite a large mismatch in the crystal structure. So whenever there is a mismatch in the crystal structure, a significant amount of mechanical strain will be developed. So you have a two dissimilar region. Whenever you are going to combine them, okay. So due to the mismatch in the crystal structure at the interface, a significant amount of mechanical strain will be developed. Okay, a significant amount of mechanical strain will be developed, and this strain effect, due to this strain effect, what will happen? There may be some oxide interface charge. Okay, there may be some positive charges present, okay, near the oxide semiconductor interface. Okay, so that total charge we are saying that that is including that electrically active defects inside the oxide, as well as due to that mismatch in the crystal structure due to the strain effect. Okay, this total charge we can say this total charge is QOX. Okay, so QX is the total amount of charge that is due to this the trap charge and the oxide interface charge, etc., etc. So if QX is the charge, so the voltage component we can write so voltage component will be Q by C, so QX by COX. Okay, so the voltage component will be QX by COX. That means you have to apply this equal and opposite amount if this is positive. Okay, so QX by COX, if this is a positive quantity, then you have to apply a gate voltage which will nullify, which will cancel its effect. That means you have to apply equal and opposite amount of voltage at the gate terminal. Let here you are getting minus 0.5, for example. I'm telling a typical value. So at the gate side, you have to apply plus 0.5 volt, okay, to nullify its effect. Okay. So those four components are basically, you can say, the components of threshold voltage. 0, 1, 2, 3, they are the major components of threshold voltage, but sometimes, especially for the nanoscale MOSFET, okay, when you are working with the submicron MOSFET with different oxide material, not silicon dioxide, this 0.4 is not negligible. You have to consider the 0.4. Okay. So combining all those things, now we are going to establish the expression for threshold voltage. Let's see the final expression. So final expression for threshold voltage. So I'm giving the name threshold voltage VT0, that is equal to the first point, see, the work function difference between the gate and the channel, that is phi ms or phi gc or VFB, whatever you can write. Okay. That is phi ms. Okay. Second component is the amount of gate voltage required to establish the condition phi s equal to minus phi f. That is the total change in surface potential will be minus 2 phi f plus of minus 2 phi f. Third component, the amount of gate voltage component required to offset the voltage developed by depletion charges. So the voltage developed by depletion charges is QB0 by COX. So what will be the component of gate voltage? Anyone? If the voltage developed by depletion charges is this, what will be the component of gate voltage? How much I will write here?
So to offset the charge, create charges.
Offset the charges, right? Offset to cancel the charges. QB0 by COX is already there. We have to cancel it. So we have to apply opposite amount, equal and opposite. Last one. Oxide and trap charge QOX by COX is voltage. So we have to apply minus QOX by COX. Okay. So that means it is coming like this: phi ms minus 2 phi f minus QB0 by COX minus QOX by COX. So that is VT0. Okay. So this is the expression we are getting till now, and again we shall simplify it, where this term VT0 is called threshold voltage at VSB equal to 0. Now actually what is VSB? VSB is called the substrate bias voltage. Okay, that means the voltage between source and body terminal. So if I draw the sketch of MOSFET, okay. So this is the gate, this is the source, this is the drain, and this is the substrate or body. So the amount of voltage applied between the source and body, so that is the VSB. So in this expression is valid only when the VSB equal to 0. That means source and body, they are at same potential. So VSB means substrate bias voltage or body bias voltage. Means the source generally, the source is grounded, so body is also grounded. They are at same potential. Okay. But when VSB is not 0, so there will be some modification in the threshold voltage. So let us see. When VSB not equal to 0, then threshold voltage is called VT, not VT0. We are saying the threshold voltage is called VT, or in some textbook it is mentioned as VTH. Okay, in some textbook it is mentioned as VTH. Fine. So what will be the change? The change will be, see, phi ms, it is a material property. The work function difference between the metal and semiconductor, it will not be affected by applying a body voltage. Or if VSB is not 0, it will not affect this parameter, it will not affect this parameter. The changes are here actually, QB0. Okay. So then the depletion charge at VSB not equal to 0 is QB. So previously it was QB0. Now I am writing the depletion charge at VSB not equal to 0, that is equal to QB. And the expression for QB, so we have QB0 expression here. So what will be the modification in this equation? So let us see. QB, the QB will be the same equation, only little bit modification will be there. Minus 2Q, oh sorry, minus already there. Na epsilon Si, previously it was minus 2 phi f. Now I am adding one term VSB. So VSB is there inside this. minus 2 phi A plus BSB. So it will affect the depletion charge QB. Okay. So then we can write the expression for Vt, it is same as phi ms minus 2 phi f minus, instead of writing QB0, I am writing QB by COX minus QS by COX. So only change is here. Okay, QB by COX. Now, if I want to write this Vt in terms of Vt0, okay, because the Vt0 expression is there. If I want to express Vt in terms of Vt0, so I can write this expression in this way. Just check phi ms minus 2 phi f minus QB0 by COX minus QX by COX. Okay, see, I have written then minus QB by COX. I have written this term extra plus QB0 by COX. Now check whether this line and this line, they are same or different. Just check it. Verify. So I am
Sir, minus,
the same or different.
sir, they are same. Minus QB by COX equals to QB lot by COX is cancelled.
So basically they are same. So
Yes,
because we are going to represent Vt in terms of Vt0. So check the first term. What is this?
Vt0.
So Vt0. So this term is Vt0 minus the second term I am writing in this way, QB minus QB0 by COX. Okay. Vt0 minus QB0 by COX. Okay. So now we are going to calculate the second term, QB minus QB0 by COX separately. Okay. So let us see. We have QB expression, this one. We have QB0 expression, this one. So can we simplify this term, QB minus QB0 by COX? So let us see. So we have QB equal to minus of root of 2QNA epsilon SI minus 2 phi A plus VSB. And we have QB0, that is minus of root of 2QNA epsilon SI mod of minus 2 phi A. So I am going to calculate QB minus QB0 by COX, this term. So just check, we can just see minus root of 2QNA epsilon SI, this term is common, okay, for both cases. Okay, so we can take this one common, 2QNA epsilon SI, okay, minus root of 2QNA epsilon SI, okay, by COX. Okay, so we can write this, we can take minus common, okay, then so we can write this part in this way, minus of root of 2QNA epsilon SI into root of minus 2 phi A plus VSB. So can I write in this way, in this expression? Root of A into B, that is root of A into root of B, I can write. Okay. Similarly, this equation we can write minus root of 2QNA epsilon SI into root of minus 2 phi A. So I am taking the first one common, minus 2qn epsilon hi by cox is there. Okay, so it is coming root of minus 2 phi f plus VSB. Okay, just a minute. Minus root of minus 2 phi f. Check whether I can write it in this way or not. Please check it. This is the expression for QB. This is the expression for QB0. Check it whether I can write it in this way or not. Verify. We are going to calculate this.
Yes, sir, it can be written.
Minus QB0. You just simplify this line and check whether you are getting this one or not. So others, please verify.
Yes, sir.
So we are
Yes,
taking
sir.
the common part. Common part means minus root of 2qn epsilon by cox. Cox is at the denominator term, so we have to take that. So this. So if I put this term here in this equation, so Vt equal to Vt0 minus of this one. So finally we are getting Vt equal to Vt0 minus, and that minus here, another one minus is there. So it will be plus root of 2qn epsilon si by cox into root of minus 2 phi f plus vsb minus of root of minus 2 phi f. Okay. So we can write this term, this root of 2qn epsilon si by cox, that is called gamma. Okay, gamma into root of minus 2 phi a plus vsp minus of root of minus of 2 phi a. Okay. Okay, so it can be written in this way. Okay. This gamma is nothing but this constant. Okay, so if I write gamma, the root of 2qna epsilon si by cox, it is called body factor. Okay, body factor or body coefficient. Okay, the unit of gamma, if you calculate, it will be v to the power half root of v. You can calculate the unit of gamma will be root of v. Okay, so this gamma basically indicates the role of VSB in the circuit. Now check this equation, the final expression we are getting, Vt equal to Vt0 plus this one. Okay, now check. If I put VSB equal to 0 in this equation, so if I put VSB equal to 0, this term inside the third bracket, it will be 0. Check. The term inside the third bracket, it will be 0. So this is root of minus 2 phi a minus of root of minus 2 phi a, so it will be 0. And Vt is just equals to Vt0. That is valid. Okay, So threshold voltage of a MOS transistor will be equal to VT0 when VSB equal to 0.